Good morning, everyone. My name is Danielle Serratos. I'm the Director Curator at the Fundy Geological Museum. Before we get started on the talk this morning, I'm going to briefly give an overview of a bit of my history in working with fossils, and hopefully this will be a bit of a buffer if we have any latecomers to the talk. So I've been at the Fundy Geo Museum for the past 2 years. My family and I immigrated from the States to come to Parsboro in Nova Scotia for this job. My family consists of a husband and two daughters, the oldest of which is about to turn 3. We're very glad, very fortunate to be in Nova Scotia with everything that's going on in the world right now. Speaking of the pandemic, this presentation is actually being broadcast from my home. My kiddos decided to give me a bit of a sniffle before this talk was scheduled. So instead of traveling to Joggins and risking sharing those germs with anyone there, instead, the Joggins crew has graciously allowed me access to their Facebook account. So hopefully everything goes well. I don't see any comments that you can't hear me or anything like that so far, so we'll proceed as if everything's working smoothly. Before coming to Canada, I lived in South Dakota, Colorado, Alaska, and Texas. I got to work on fossils in each of those states, and they all impacted me and my career differently. But oddly enough, the most time I've spent on any one fossil was from Montana, a state I've never actually been to. While in grad school in Alaska, my thesis advisor was contacted about a long-necked marine reptile from the Cretaceous period, which was about 70 million years ago, that had been found by an elk hunter. The specimen was collected and shipped to Alaska so that I could clean it up and write a paper about it, which I did. While my experiences so far have been limited to North America, paleontology truly is a global science. As Madame Curie would say, nothing in life is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less. There's a lot of reason to fear the unknown, especially with what's going on in the world right now. But hopefully, paleontology isn't something that's ever to be feared. In the spirit of understanding more and fearing less, we are going to talk about fossils today. Fossils tell us about past life, how life has changed over time, past environments, and how climate has changed over time, and the role of natural disasters in those changes. On the left, you can see a stylized phylogenetic tree. It shows how all life on the planet is related to one another and tells us at a glance that humans are more closely related to cows than we are to kangaroos, just as an example. Fossils are evidence of past life. So there's many different types of fossils. The first one that I like to talk about is carbonized fossils. These fossils are technically a carbon film remnant of the original organism and can preserve very fine details, but they're basically in 2 dimension. The carbonized fossil, like the fern at the upper left corner of the images, are a result from being buried very quickly and not being exposed to oxygen while being fossilized. So that's a carboniferous fern from here in Nova Scotia. At the top right corner, you'll see what we commonly call a body fossil. So body fossils can be skeletal bones, shells, teeth, seeds, plant material, etc. The image that you're seeing at the top right is actually a hybodont shark tooth from Wasson Bluff. That's just down the street here from Parsboro on the Bay of Fundy. So, this 200 million year old freshwater shark tooth is actually found at the same site that we do our dig for Canada's oldest dinosaur site. So, there's actually a lake bed that's fossilized and deposited next to those sand dunes where we find those dinosaur bones. Oftentimes, bones that are fossilized will be replaced by minerals, but teeth, like this Jurassic shark tooth, have not been altered over millions of years. We'll talk more about that in a bit. Another type of fossil are the trace fossils, like footprints, feces, coprolites, burrows, things like that. The tree stump in the lower left picture is actually a cast, which I'll mention here in a moment. But what you can't really see in this picture is that running between all of those stumps that you see in cross section next to our staff member's hand are the fossil trackways of horseshoe crabs. So this fossil site is actually, it was discovered this summer, and we just excavated this fossil last week with a crew. It was a very fortunate experience. We actually took out a rock saw to this site, thinking that we'd have to remove the entire section to get that fossil out. And turns out we showed up at the site and it had fallen out of the cliff already, most likely the night before, and stayed in one whole section. So we were able to just lift that massive block onto the back of a truck bed and take it back to the museum for further research. The last different types of fossils that I'm going to talk about today are molds and casts. So I mentioned that the tree stumps in that lower left picture are casts of the original trees. In the lower right image, you can actually see the lepidodendron, which is a mold of the tree that used to grow in what is now Joggins, but that would have been 300 million years ago. Natural molds are impressions of the organic remains, and natural casts are sedimentary fill-ins of a natural mold or the organic remains if they were originally hollow, like the inside of a shell. Sylvia Earle is a pioneer in modern marine sciences, but she has some excellent quotes that also apply to the field of paleontology. She said, rather than be afraid of evolution and try to stifle inquiry, people should revel in the joys of knowing and find a serenity and a joy in being part of the rest of life on Earth, not apart from it, but part of it. Well, this is, I think, a poignant point that really opens up, how we should be discussing evolution when we talk about it with the general public. As scientists and paleontologists, we tend to dig into the minutia of what evolution is. But at the end of the day, it's the unifying scientific theory that says we're all related to each other if we look back far enough. Evolution is an incredibly complex story. With every new fossil find, we have the opportunity to learn more about how life has evolved on this planet over the past few billion years. I know a lot of people struggle with the idea that all of life on Earth came from microscopic bacteria, but when you put it into the context of geologic time, it becomes easier to understand. For example, if we condensed all of Earth's time into just 1 year, humans would have only been around for the last 12 minutes for that entire year. Another way to think of it, complex life, everything from trilobites to dinosaurs, and the very first plants to household cats, have only been around 11% of the time Earth has been a planet. By identifying fossils and categorizing them into groups such as fish, birds, and mammals, we're able to better understand how life has changed over this vast amount of time. Sometimes this story takes weird turns. take whales, for example. Whales are what we would call secondarily aquatic organisms. That means that when you trace their evolutionary history back through the fossil record, you'll find that their immediate ancestors lived in the water, their ancestors to that walked on land, and their ancestors lived in the water. Evolution is a complex story, and we're learning more about it every single day. So, putting that life story into context is not the easiest thing to do. However, we've made a lot of progress over the past couple hundred years. Fossils that have helped researchers build the geologic timescale. In the past, a method called the principle of faunal succession was used to create the first geological timescale. This principle states that certain fossil species always appear and disappear in the same order, and that once a fossil species goes extinct, it disappears and cannot appear in younger rocks. For example, in this diagram, here we see the brown coral is of an unknown age, but is only found globally in the same rocks with both the blue and orange ammonites. The gray arrows tell us when these fossils first appear and when they disappear or go extinct. By having a global understanding of when and where these fossils appear and disappear, we can see that the brown coral has to be the same age as any rocks that have both the blue and orange ammonites in them, no matter where in the world they're found. Once scientists had this info gathered for thousands of fossils, they could start applying ages to them. And then radioactive isotope dating, otherwise known as absolute dating, came along and verified what fossils had already told us about the age of the Earth and life on it. Now, we're going to switch gears a bit here and move into talking about paleoclimates. There are actually many ways that fossils can tell us about paleoclimates, or the global environment that was around millions of years ago. One of the best ways to do that is to take the Earth's temperature via the oceans. Seawater is the single best indicator for how healthy the planet is, and ocean temperatures are the easiest way to get a global picture. Fossils like forams, or foraminifera is the proper term, diatoms, ostracods, corals, and even mollusks can tell us about how warm the oceans were when those organisms were alive. The picture you're seeing here is actually a really cool way that we combine STEM fields. You might have heard that term, science, technology, engineering, and math, with art, sometimes called STEAM for short. The picture you're seeing here is microscopic art of arranging diatoms, these microscopic marine fossils, which are single-celled algae and whose bodies are made of silica, which is the same element that makes up the majority of the terrestrial plates, what we consider the continents on the planet. So, putting that climate research into context, we've discussed some of the ways that fossils can transport us back in time. And we know what those paleo environments were like, but how does that help us for today? Well, just last week, a new study was published, and the figure you're looking at now is from that research. They looked at global climate changes over the past 66 million years. So, from now until when the dinosaurs went extinct. And they found that while we're still technically in an ice age, the world's temperature is rising at an exponentially faster rate than it has ever occurred naturally in the past. Earth is expected to go from an ice age to a hothouse climate over the course of hundreds of years instead of the millions of years it took to happen naturally since the age of dinosaurs. We only know this due to those fossil forams having been preserved globally over the past 66 million years. And the more we know about these previous environments, the better prepared we can be to expect what is to come during the next few generations. See, when we look at the fossil record and we see how mass extinctions occur and species die out and other animals come in to take the opportunity of new resources being available, we can start to analyze statistically what factors are most important and most beneficial to that recovery of a species or a group of animals in those situations. Now, this all seems kind of doom and gloom, and that's often the case when we talk about global climate change. However, Rachel Carson said it best when she said, "There's something infinitely healing in the repeated refrains of nature, the assurance that dawn comes after night and spring after winter." So, when we talk about natural disasters and the mass extinctions that result from them, um, they are the main reason that life looks totally different today compared to the fossils that we find in the rock record. Mass extinctions, however, also free up ecological niches that allow for species to diversify quickly once their competitors for resources are no longer in the picture. So, the easiest example of this would be talking about the end of the age of dinosaurs, that KT extinction event. So, yes, we know that most of the dinosaurs went extinct. There is the exception with what are now birds, because birds, as you may know, their ancestors were theropod dinosaurs like T Rex, Allosaurus, Velociraptor. So, not all dinosaurs are extinct, they're just very different looking today. But by and large, that was a mass extinction that wiped out most of the dinosaurs and, in fact, most of life on planet Earth. However, the small rodent like mammals that were scurrying around the feet of giant dinosaurs 65, 70 million years ago survived that mass extinction event and were able to diversify immensely into the variety of mammals and other animals that we see alive today. Now, it is important to remember that recovery of species, groups, taxa, all of those does take time. It's not something that happens overnight. And there's going to be a lot of changes and even micro extinctions along the way. Many fossil groups have gone extinct. In fact, we estimate that 99% of all species that have ever existed on the planet has gone extinct. But if we look around the planet, there are still millions of species here, most of them thriving despite all the world's troubles, including the ones that humans have introduced. Natural disasters and mass extinctions have taken a massive toll on life on Earth, but they keep coming back in new and exciting ways. In fact, we're discovering new species every day, like the 30 plus new species identified near Australia earlier this year, some of which are shown in the image in the lower right of your screen. Now, the best reason why fossils are so important, I think, and take this with a grain of salt, it's my opinion, but I think the best reason that fossils are important is because they're great for science communication. Everyone loves a mystery, everyone loves a monster story. Fossils and paleontology are gateway science. They're captivating to the public and encourage science literacy through education and entertainment. It's no coincidence that some of the most famous modern scientists are either paleontologists or experts in space. Whether it be prehistoric monsters bursting forth from secret labs or aliens descending from space, both fields share the constant sense of discovery and speculation about the unknown. Now, fun fact, did you know that we are closer in time to T. rex than T. rex was to Stegosaurus? T. rex and humans are separated by roughly 65 million years, and T. rex and Stegosaurus are separated by 80 to 90 million years. This is the type of science communication that I love sharing with our guests at the museum. This tends to really open up people's perspective of just how big time is. Geologic time, deep time, however you want to talk about it, it is a massively complex idea that is really hard to grasp. And part of the reason that we have museums all over the world is so that we can constantly learn how to better explain these big ideas, these big concepts, and hopefully encourage a love of science in our guests along the way. Well, I hope you have enjoyed this talk. I don't see any questions in the comment section, so if you have any questions, feel free to leave them in the comments after the video has ended, or feel free to look me up on Twitter or go to, if not the Joggins Facebook page, the Fundy Geological Museum page. We're always happy to answer your questions about fossils, geology, rocks, minerals, and Nova Scotia in general. Thank you so much for your time and attention, and I hope you have a great day, everyone.